Hello class, I'm coming to you today with section 4.5, Limits at Infinity. Let me get ready to share my screen and we will get started. Okay, so 4.5, we're looking at limits at infinity. We'll also be looking at some finite. Specifically, we'll be looking at some finite limits at infinity and some infinite limits at infinity, and also determining if we have anything as far as asymptotes, mainly horizontal. All right, so limits at infinity. This section discusses the end behavior of a function on an infinite interval. Let's consider this graph. F of x equals 3x squared over x squared plus 1 is what's shown here in this figure. Okay, as you can see, at each end, it appears that the function is kind of flattening out towards this horizontal line. Okay, so towards the left, we're approaching, or we're headed, x is approaching, or x is headed towards negative infinity. And towards the right, x is also headed towards infinity, but positive infinity at the right end. And you can see as x approaches negative infinity, the function is approaching 3. It's getting closer and closer to 3. And you will, let me say this, you will use your calculator looking at examining the graphs quite a bit in this section. You'll find that makes it a bit easier. So again, don't be afraid to use your calculator, your resources that are available to you. So as x approaches positive infinity on the right end, the function f of x is headed or approaching 3. So graphically, we can see that the function appears to approach 3 as x increases without bound towards the right, or as x decreases without bound towards the left. You can come to the same conclusions numerically as well by examining the function in a table. So looking at x values from the number line, negative infinity to the left, positive infinity to the right, and then choosing some values, negative 100, positive 100, negative 10, positive 10, negative 1 and 1, and then we got 0 in the middle. So that we can examine what's happening as we get closer and closer, as x approaches larger and larger numbers, or smaller and smaller numbers towards the left, and larger numbers towards the right. We're seeing what the function is approaching, okay? And f of x, the function is approaching 3. We can see that numerically from the table, okay? So what does this all mean, you might say? So both of those, both of those graphs, or not both of those graphs, the graph and the table show or suggest that f of x is approaching 3 as x increases without bound, and likewise, it approaches 3 when x decreases without bound. These are what we call limits at infinity, okay? So you can see how we write our limit notation here as we have in the past, but what's different is x is approaching negative infinity, or x is approaching positive infinity. So it's the limit as x approaches negative infinity of f of x equals 3, and then this is where the limit as x approaches positive infinity of f of x equals 3, or limit at negative infinity, limit at positive infinity. So to say that a statement is true as x increases without bound means that for some large real number m, the statement is true for all x values in that interval, for all x values greater than m. Okay? So that just brings us to the definition, just kind of thinking about it in terms of, in a general term. Let L be a real number. It says the statement, the limit as x approaches positive infinity of f of x equals some limit value L, means that for each epsilon greater than 0, there exists an m greater than 0, such that the function minus L is less than that epsilon value, but x is greater than m. So again, this definition kind of reminds me of one of our early definitions when we first started looking at limits, okay? You won't have to necessarily apply it as we did before, though. We'll actually be evaluating the limits here. We won't necessarily be proving it or applying the definition per se. But that does satisfy, statement one does also mean the same or can be written the same even when x is approaching negative infinity, either one. Excuse me. And then you've got a graph of that just showing that, excuse me, the function there will be, I'm sorry, can't talk. There will be some value, some limit value that will exist provided that the rules or the definition works out. So let's take a look at a few properties of limits and then we'll look at examples. So here, definition of a horizontal asymptote. That previous example, that first example, it actually did have a horizontal asymptote. The horizontal asymptote was the limit value. And that just leads us here to this definition. So recall that previous figure. The graph of f approaches the line y equals L as x increased without bound and as it decreased. As x decreases without bound. The line y equals L is called a horizontal asymptote. So the line y equals L will be a horizontal asymptote if your limits at infinity equal L. So, for example, if we have the limit as x approaches negative infinity of some function. If that equals this value L, then that means when you can write the line y equals L, whatever that value is, it would be the horizontal asymptote of that function. And same thing if the function, or I'm sorry, if x is approaching positive infinity, works the same. Okay, we got a couple of properties also that apply as they did before, so they still apply even when you're dealing with limits at infinity. If you got a sum of two functions, a limit of two sums, or the limit of a sum of two functions, then you can basically separate them apart or place them having their own limits individually and evaluate each. Likewise, if you have a product, you can evaluate each limit individually and multiply together. And for some reason, my notation looks like this is some together line, but it shouldn't be. It should be separate. The limit of the first one times the limit of the second value. Okay? We also have some other properties or another theorem that relates limits at infinity and rational numbers. So the first one says if R is a positive rational number and C is any real number, then the limit as x approaches infinity or negative infinity of C over x to the R will equal 0. Okay? So basically, if you've got some constant and you are dividing it by some big number, okay, because x to the R power represents a number that is in squared, so pretty significantly bigger than C, then that function or that limit value of that function will equal 0. Okay? It will equal 0. So, like for example, if you had limit as x approaches infinity of, let's say, 5 over x to the 10th. Think about it. As x gets bigger, this gets exponentially bigger because this is x to the 10th power. So if you're dividing 5 by some exponentially large number, this limit will approach 0. Even if you are dealing with a negative infinity, still got some constant, let's say 5 over x to the 10th power. Again, plugging in infinity, but then squaring it, or not even squaring it, raising it to some power, makes that number get bigger. And again, you're dividing by a small number by a much larger number. Okay. Now this one is valid when x is less than 0. Take note here that the second limit here is valid when only x is less than 0, or your r value is an even power. Okay. So either x needs to be like a negative or less than 0, and then your r, well, actually it says it right there. Okay. Another one, e to the x is equal to 0 as x approaches negative infinity, and the limit as x approaches positive infinity, e to the negative x is also 0. So you might want to memorize those, but you can plug in examples or numbers and see what you get and verify that it is approaching 0. Okay? All right, let's look at a few examples here. So on part A and B, at the very top for example 1, it says find each limit. So right here I've got the limit as x approaches positive infinity of 5, a constant, minus 2 over x squared. All right, so what I'm going to do is separate this difference of these two terms, give them each their own limit function or limit expression. The limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared. Okay? Well, the limit of a constant is always a constant. It's always that constant. Now here, you want to look at this as infinity gets bigger, as the denominator gets bigger, placing numbers approaching infinity here in the denominator. This is going to approach 0. As this denominator gets bigger, you're dividing a much smaller number by a much larger number. This heads towards 0. So 5 minus 0 is just 5. Okay? All right, let's look at this one. The limit as x approaches infinity of 3 over e to the x. Well, the first thing I'm going to do, instead of having this as a quotient, I'm going to express it by moving e to the x to the top so that I can think about that previous theorem. So the limit as x approaches infinity of 3e to the negative x. Okay? Well, this is a constant. And so the limit of a constant is just that. Or it's just going to be, actually you can consider this a scalar product. Okay, so it's almost as if you can pull that 3 out front from our previous limit rules or properties that we looked at way back in like chapter 2, I think. So we can pull that scalar multiple or scalar product or scalar constant out front. It's just a number that's multiplied to the e to the negative x. And then we want to evaluate the limit as x approaches infinity of e to the x. So as x gets bigger, okay, as we plug in bigger and bigger numbers here, e to the negative x heads towards 0. So this would be 3 times 0, which is just 0. And again, I am referencing for that limit value, I am referring back to this theorem, 4.10, that gave me that as a solution. Okay? So I just brought the e to the x to the top by making it e to the negative x. And then the 3 just came out front because it was a scalar product. Okay? All right, here's another one. So this one, we want to look at it in terms of what x approaches. Okay? Now, here's the thing with this example. You may have something that we'll look at, I know, in detail a little later, but I want to mention something to you now. I don't see it in my notes. I may have to pull up the textbook in class. But, okay, so here's an issue whenever you're evaluating limits at infinity. you could have something called an indeterminate form where you're unable to determine the value of the limit, and you may have to do something else in order to rewrite it in a way that allows you to determine the limit. So indeterminates are spoken about. I don't think they're in your homework too much, but they are spoken about in the text, and I may talk about it a little bit more in class, but I just want to give you a little background on this one. So if we're looking at this one, this limit as x approaches infinity of 2x minus 1 over x plus 1, take a look. If we were to actually replace x with infinity or numbers really, really big, as x approaches infinity on top and bottom, or in the numerator and denominator, then both approach infinity. If you were to replace infinity on top, or some really big number on the top here, and some really big number on the bottom here, you'd have 2 times infinity minus 1, infinity plus 1, so you just have infinity over infinity, basically. This would result in an indeterminate form. And what that just means is it's resulting in a form that you're unable to evaluate with one of those previous theorems. Okay, you're unable to evaluate it. You're not sure. You can't determine it. We don't know what infinity divided by infinity is. Okay, we can't necessarily say that it's 1 because infinity is a number that you really don't reach. So we say this is an indeterminate form, and it's the indeterminate form infinity over infinity. You could have negative infinity over negative infinity, okay? That's also an indeterminate form. So what we have to do is rewrite it in a way that allows us to evaluate the limit. Rewrite the limit function in an equivalent way that we can solve. Okay? So I've got limit as x approaches infinity of 2x minus 1 over x plus 1. Okay? So what I'm going to do is I'm going to try to set up an expression where maybe I've got let's create a fraction on top. Let's make it, normally we try to make it less complex, but we're going to actually make this more complex. Let's say we multiply the top here by 1 over x and the bottom here by 1 over x. As long as you multiply top and bottom by it, it's still legal, okay? Because you're still dealing with an equivalent form. So the limit of x approaches infinity. This gives me 2x minus 1 over x on top, and it gives me x plus 1 over x on bottom. Okay? And I'm taking the limit of top and bottom. Keep that in mind. So what I'm going to do is I'm going to break the top apart. I'm going to break the bottom terms apart. So I'll have 2x over x minus 1 over x. And then I'll have x over x plus 1 over x. Okay? That allows me to pull that constant away from the x term. Because see, before it was 2 times x, so it's been 2 times infinity basically, which is still just be some infinity, just double. But what this allows me to do is now I can actually remove the x that's with the 2 and remove the x here and make that just a 1, allowing me to actually solve this. So I've got 2, because this x cancels there. minus 1 over x on top. And I've got 1, because this x cancels there, plus 1 over x on the bottom here. Now I'm ready to evaluate the limit, because now I don't have to worry about getting infinity over infinity, okay? So now I've got the limit of a constant over, so the limit of a constant minus the limit of 1 over x over the limit of another constant plus the limit of 1 over x. Okay? So here, now that we've just got a constant up top, I don't have infinity up top anymore. Now I can actually evaluate this. So this is like 1 over some huge, huge number. So this approaches 0. And again, this is 1 over some huge, huge number. So this approaches 0. And the limit of a constant is always just that constant. So this is 2 minus 0 over 1 plus 0, which is 2 over 1, which is just 2. So the limit of 2x minus 1 over x plus 1 as x approaches infinity is simply 2. We would not have gotten that otherwise. Looking at it in its original form, I would have said infinity, or I would have said 1, infinity over infinity. But that doesn't work like that. And neither does canceling out infinity over infinity and just leaving 1. That doesn't work either. It's an indeterminate form that you have to figure out how to rewrite so that you can evaluate it, okay? And again, sometimes it helps to look at the graph even on these. Don't be afraid to use your calculator. You are not cheating when you are looking at the graph, okay? So I'm just going to look at the function. I can't put the limit actually in there. I don't really want to do that. But I just want to look at the graph of the function and see what I've got here. Maybe it'll reveal something to us. You never know. Let's hit graph, and I may have to adjust it. And it looks like I can see what's kind of happening here. Let's go zoom standard. And I think you'll be able to see here. And maybe even looking at the table. So take a look. As x approaches positive infinity, so we're looking as x goes to the right towards positive infinity, we want to see where is this function going in this direction. Okay? Let's say we adjust our window to where we reduce the x min, because I don't need to see much on the left side. Remember, I'm focused on x approaching positive infinity. So let's maybe make that like -3, and let's make that 20. And see what we got now. Yep, you can see how it's rising slowly towards some number here, but it's not growing fast. It's not getting bigger. It's not going up, it doesn't look like. So let's press second table and see what's happening here. There it is. Take a look. As x gets bigger and bigger, look at what y is doing. Y is getting closer and closer to 2. Which is our limit value. Okay? You can see how thinking of this as infinity over infinity would have had us totally wrong. Okay? So that is why you have to think about these different forms, even the indeterminate form. You can't figure out what infinity over infinity is. Okay? So that's one form that we could not figure out in its original, for this particular original form equation or function. All right, let's look at some more here. How about these? And then I'll pull up some homework questions and see what we got. This section is not as long. I don't think it'll take you as much time. So we'll look at this one. All right, so here it says find each limit. So again, each of these, as x approaches infinity, each one of these cases is going to give you the indeterminate form infinity over infinity. 2 times infinity over 3 times infinity is still infinity over infinity. Likewise here and here, likewise here and here. So each case results in the indeterminate form. And remember, you can look up indeterminate in your textbook. Remember that you got the ebook. They may discuss it in the video, but I know our videos for our textbook are not as detailed as we would like. So you may actually need to go to the textbook if you're questioning the indeterminate form. Okay? If you're not sure, or if you need to kind of look over that. But each of those results in an indeterminate form, infinity over infinity. We say indeterminate because we have no idea, evaluating it as is, what the actual limit value would be. Infinity over infinity is not an answer. Okay? So we have to rewrite these. And what I'm going to do is take note of the fact that each denominator has x squared in it. So I'm going to multiply, well, technically I guess you can say I'm going to divide top and bottom by x squared, which means I'm going to multiply top and bottom by 1 over x squared. So we're going to rewrite each function, or each limit value, into each function, because they're functions. And this is only an issue, the indeterminate form is an issue when you have irrational functions, okay? So we're going to rewrite each function by multiplying, I guess you could say dividing by x squared, but I'm just going to say multiplying by 1 over x squared. Okay, so I've got a, I've got the limit as x approaches infinity of 2x plus 5 over 3x squared plus 1. So as is, it won't work. So what I'm going to do is I'm going to multiply top and bottom by x squared, or 1 over x squared. Okay? So what that's going to do is, I'm going to put my limit out here as x approaches infinity. That's going to have the top as 2x plus 5 over x squared. And then on the bottom, 3x squared plus 1 over x squared. Okay? Now simplifying that, or cleaning that up. So here on top, still got my limit, let me write that. On top, I'll have 2x over x squared plus 5 over x squared. And on bottom, I'll have 3x squared over x squared plus 1 over x squared. Okay? And so we're going to see what will our answer be. What will we get for this? What will our answer be for this problem? So let's take a look. Keep in mind, x squared over x squared cancels out. So this is the limit as x approaches infinity of, and then this x cancels with one of those, 2 over x plus 5 over x squared over 3 plus 1 over x squared. So now we're able to evaluate this. So as the limit, as x approaches infinity, I should say, the limit of 2 over x will approach 0, because as this denominator gets big, 2 divided by a really big number heads towards 0. This one, the same thing, heads towards 0. 5 divided by a really big number squared is still a 5 divided by a really, really big number. So that approaches 0 as well. Here, the limit of a constant is just that constant. And then this approaches 0 as well. 1 divided by some really big number is 0. So you end up with 0 on top, and you evaluate the limit, 0 on top, 3 on bottom, which is just 0. So the limit as x approaches infinity of 2x plus 5 over 3x squared plus 1 is actually 0. Okay? Let's go ahead and look at B, and we'll try to look at C as well. The limit as x approaches infinity 2x plus 5 over 3x squared plus 1. Actually, that's 2x squared plus 5 over 3x squared plus 1. So again, I'm going to multiply top and bottom by 1 over x squared. So I end up with the limit as x approaches infinity of 2x squared over x squared plus 5 over x squared over 3x squared over x squared plus 1 over x squared. Okay? So let's see what we get here. So these x's cancel. Okay? So you got the limit as x approaches infinity. That's just a constant 2. And you got plus 5 over x squared. And then on bottom, these x squareds cancel as well. So you just got a constant 3 and then plus 1 over x squared. Okay? So as x gets bigger, 5 divided by some really big number heads towards 0. Same thing here. As x gets bigger and bigger, 1 divided by some really big number heads towards 0. So the limit of a constant, because those are just zeros, those limits, it's still just a constant. The limit of 2/3 as x approaches infinity is still 2/3. Okay? One more part here I want to look at. Part C here on this one. Again, we're going to have to rewrite it in an equivalent form because as they are now, they end up giving us infinity over infinity, the indeterminate form. Let's back up here. So we've got 2x cubed plus 5 over x squared, and then 3x squared plus 1 over x squared. All I did was this step, but I just jumped here. I didn't write that step where I'm multiplying top and bottom by 1 over x squared. I did do it, and you can see that I wrote top and bottom, the original problem, top and bottom over x squared. Okay? All right, now, when we carry it through or simplify it, clean it up a bit, the limit as x approaches infinity, we've got 2x cubed over x squared plus 5 over x squared. I got another pen. Starting to swell or something. All right, then we've got 3 over x squared, and then we've got 1 over x squared. Okay? So what's going to happen? Here, x squared is going to cancel out with 2 of those. So let me rewrite limit as x approaches infinity. So right here I've got 2x. Then I've got plus 5 over x squared. On bottom, x squared cancels with x squared. I've got 3. Then I've got plus 1 over x squared. Okay? So as x gets bigger, both of these approach 0. So 5 divided by a really big number approaches 0. 1 divided by a really big number approaches 0. So what we need to focus on is the limit as x approaches infinity of 2x over 3. Okay? So think about it like this. As x gets really big, you're just multiplying it by 2 more. So you're doubling it. So if it's already big, it's twice as big. So this is still infinity. Okay? So the limit is infinity. Or in other words, it does not exist. There is no limit. Okay? All right, let's see what else we've got here. So some guidelines on this next page here. Guidelines for finding limits at positive infinity or negative infinity of rational functions. If the degree of the numerator is less than the degree of the denominator, then the limit of the rational function will be 0. Okay, so let me just give you an example. If you have the limit as x approaches infinity of x over x squared. There you go. There's one. Okay? Something like that. That would be 0. For number 2, it says if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. And we saw that on the second example where the limit value was 2/3. And then on the third one, it says if the degree of the numerator is greater than the degree of the denominator, then the limit does not exist. There isn't one. Okay? All right. Okay, so I've got some more examples here. A function with 2 horizontal asymptotes. This one talks about a special problem, a special function. It's called the logistic function. On this previous page, I just showed you, kind of introduced it to you, how we got it. Okay, but you don't have to worry about how we got it necessarily. This is a function where we're asked to show that the logistic function has different horizontal asymptotes at each end. You won't have to show, you won't have to necessarily prove or anything like that, but what you would do, you could look at the sketch, and then, of course, you could look at the sketch, but then you could also examine the table, look at the table numerically, the table of values. So look at the sketch on your calculator. And look at table of values numerically. Okay? So we'll look at that. We've got our function is 1 over 1 plus e to the negative x. So I'm going to look at the limit for both of these. The limit as x approaches negative infinity of 1 over 1 plus e to the negative x, and the limit as x approaches positive infinity of 1 over 1 plus e to the negative x. So we're going to look at a table to kind of see what's happening. So I'm going to look at it from the negative infinity way and the positive infinity way. Now I probably won't actually have values for positive and negative infinity, but I'm just putting that there. What we'll be looking at, let's say, is negative 100, and let's say positive 100. Then let's say negative 10 and positive 10. 5 and negative 5. And then let's say negative 1 and positive 1. Okay? So bear with me here. I'm not going to necessarily show you each time I plug it into my calculator. I'll do it once to just see what we get, and then I'll write the numbers down. I've already put them in. So 1 divided by parentheses 1 plus e to the negative 100. Because it is negative, but then we're going to put in a negative. So I guess I need to just put in 100. And I get almost 0, basically. This little e to the negative 44 towers, that is scientific notation. That means you need to move your decimal 44 places to the left, and in those 43 places, because you're going to jump over the 3, that's one place. So in those empty 43 places, you're going to put in a bunch of zeros. So that means x at negative 100, evaluating the function where x is negative 100, leaves you with 0 there. Okay? Plugging in 10, or negative 10. I'm going to delete, insert, negative. I should also get 0. Okay, hold on. Let me double check that. 1, oh, no, I'm sorry. Positive 10. Because the number is negative and the function is negative, so that should be positive 10. And that is also 0. 4.5 e negative 5 means you take your decimal and you move it 5 places, 1, 2, 3, 4, 5, and in those empty spots, you have to put in zeros. So when x is negative 10, you get 0 there as well. When x is negative 5, let's see what we get. So where I have 10, I'm going to replace that with 5. Uh-oh, let me delete that 1. All right. So we get 0.00669. So 0.007. We round that to 3 decimals. Plugging in negative 1. All right. So again, that 5, well, that 1, I should say, will go in, but it's already negative, so that's going to be a positive 1. We'll hit enter. So here we get 0.269. All right, let's see what we get with plug in 1. We got that. We got plug in a positive 1. Oh, but the function is negative right there. So I'm plugging in a positive 1, but that's a negative 1 when it's all said and done because of that sign. So this is 0.731, and I plug in 5. I'm going to recall that. And plug in 5. Type over the 1 to make that 5. Hit enter. I get 0.99. And I plug in negative 10. Insert. Delete there. All right. We get 0.99995. When we plug in 100. We get 1. So we would plug in 1,000. Let's say we did that. 1. 10,000. 1. Okay? So, as x approaches negative infinity, the function, the logistic function, is headed towards 0. And as x approaches positive infinity, the logistic function is headed or equals 1. So they have different horizontal asymptotes. Each end has a different horizontal asymptote. And the end behavior, therefore, approaches different values. Behavior. Okay? All right. All right. These two examples, limits involving trig functions. Here, the first one, the limit as x approaches infinity of sine x. Well, as x approaches infinity without bound, sine x just keeps oscillating. Let me show you what I mean here. Remember, one full period for sine looks like this. And it goes up here to 1 and down here to negative 1. Well, it just keeps on doing that over and over as x approaches infinity. It keeps oscillating. So as x approaches infinity, or increases without bound, sine x oscillates, kind of takes turns, going from negative 1 to positive 1. It oscillates between negative 1 and positive 1. Therefore, the limit does not exist. limit of sine x does not exist. Now, the limit of sine x over x, that might exist. Let's take a look at it. So what we're going to do is start out looking at sine x. Let's say because sine x lies between positive 1 and negative 1, then we can actually show something like we can actually do something to each end and the middle, and it still be equivalent. So we can actually maybe divide by x, like we see in the middle here. And this is actually going to be allowing us to divide each end here by x as well. Okay. And so we're saying since sine x is somewhere between negative 1 and 1, sine x over x is somewhere between negative 1 over x and positive 1 over x. So if we can evaluate the limits at each of these ends, and they actually be the same, then we can say sine x is also the same because it's in the middle of them. And that's by something called the squeeze theorem. That's actually by the squeeze theorem. Don't get caught up in that name, but I just want you to be aware that you might see this limit, and if you'll just remember that it's just 0, you'll be good. But I'm just showing you why it's 0. So what I'm going to do now is I'm going to consider each limit as x approaches positive infinity of 1 over x, the negative I should have said, and the limit as x approaches positive infinity of 1 over x. So as x approaches positive infinity of negative 1 over x, this gets bigger and bigger. 1 or any number divided by a really, really big number approaches 0. Okay? And then negative 0 is still 0. Same thing here. 1 divided by some really, really big number approaches 0. So therefore, if sine x over x is between negative 1 over x and positive 1 over x, and those limit values are both 0, then by the squeeze theorem, sine x over x is also has a limit value equal to 0. Okay? So that equals 0. This one is not exist. All right. All right, let's see what else we've got here to talk about just a little bit in this last section. In 4.5, we will look at 4.8 also. I'll come back with another video for that. Many functions do not approach a finite limit as x increases or decreases, which we just saw on the previous problem with sine x. So, for instance, no polynomial function has a finite limit at infinity. The next definition is used to describe the behavior of polynomials and other functions at infinity. So, in other words, there are some functions that just do not have a limit value. Okay, they do not approach some finite limit value, and these definitions will, or this definition, I guess, will kind of help you to kind of understand that, I guess. It says, let f be a function defined on the interval. Okay. The statement, let f be a function defined on an interval, a to infinity. The statement, the limit as x approaches infinity of f of x equals infinity, means that for each positive number m, there is a corresponding number n, such that f of x is greater than m where x is greater than n. Okay. Similar functions can be given for these statements. So basically, it's just saying that there are some. This is just a definition. There are some limits or some limit values or some limits of functions, polynomial functions, do not have a finite limit value. Okay, that is the case sometimes. So here are a couple of examples where that may be a situation, and you can actually look at the previous rules, the guidelines here for finding limits at positive and negative infinity of rational numbers, because I do think both of these are rational, the ones I'm going to look at. So remember, if the numerator has a degree that's lower than the denominator, then the limit value is 0. Okay? If they're equal, then it's equal to that particular leading coefficient, ratio of the coefficients. And if it's greater, then it doesn't exist. So number 3 is the main one I wanted to take note of, because take a look at these. According to the rule we just saw, these limits shouldn't exist, okay? And looking at the previous property where we had indeterminate form, this would be infinity over infinity. And so you would have to work with that to get it to a different or an equivalent form so that you could evaluate it. So we can notice, though, that the higher degree, or numerator, I should say, has higher degree. So technically the limit does not exist for either of these, because it's the same case for both. Limit does not exist. But again, if you were not sure, you didn't remember that guideline, right now this is indeterminate, infinity over infinity, so you would have to probably divide out by something. I'm going to say divide out by an x, but it's still going to work out to where you're going to get does not exist. So if you divide out by the x, and you're trying to write it in an equivalent form, 2x squared minus 4x over x, and x plus 1 over x. Okay? So this becomes a limit as x approaches infinity of 2x minus 4 over here 1 plus 1 over x. So the numerator, you were able to cancel out the x on the bottom, or the x on top with the x on bottom here, and one of those x's there as well. And then on the bottom, you end up with x over x, which is 1 plus 1 over x. So as x approaches infinity, this approaches 0. So you've got, and this heads towards infinity. So you've got 2 times infinity minus 4 over 1 plus 0, which is just 2 times infinity, which is just infinity, which does not exist. Okay? Very similar to a previous problem we looked at. Same thing is going to work out here. It's going to work very similarly. So you'll basically end up with the same limit value. The only difference is you're approaching x, or x is approaching negative infinity. So you would simplify it the same way, and you would end up with 2x minus 4 on top, and on bottom 1 plus 1 over x. Okay? And then you're approaching negative infinity. This would approach 0 automatically. Here you would have 2 times negative infinity. And then over 1, I guess you can say, minus 4. You still have negative infinity, which does not exist. Okay? All right. Like I said, I don't think you'll have really too much trouble with this section. I hope that you find this section to be a bit easier. what I'm thinking. But I will answer any questions that you have. I'll answer those in class. See you soon.